Have you ever wondered where our solar system truly ends? Not in the way a map ends with a bold line, but in the way a memory fades, gently, quietly, into something unknown. Well, you see, we grow up learning the names of planets, reciting them like a comforting poem. Mercury through Neptune, perhaps Pluto if you remember it that way. And we imagine that somewhere out there is a final boundary, a cosmic fence that says, this is it. Beyond this point, you are no longer home. And yet, and that's the thing, nature rarely works like that. There are no sharp edges in the universe, no walls you can touch, only gradual transitions, whispers, rather than declarations. As we move away from the sun, step by step, the environment changes in ways that are almost unimaginable. Temperatures fall, light thins, time itself seems to stretch, becoming less about days and nights, and more about slow, patient motion. You see, no human has ever looked back at the entire solar system from the outside. We've never seen our cosmic neighborhood as a whole. And I suppose that should make us pause, because every probe we send, every signal that drifts outward, is not just a machine moving through space. It's a question we are asking how far the influence of our star truly reaches, and what happens when it finally lets go. Each step away from the sun is like leaving the warmth of a fire and walking into a vast, dark field. The physics changes. The rules feel unfamiliar, and perhaps quietly, so do we. This journey to the edge of the solar system is not just about distance. It's about testing the limits of our science, our technology, and our imagination. It's about discovering whether the idea of an edge even makes sense at all. And when you really think about it, it's also about us, trying to understand our place in a universe that never stops expanding our sense of wonder. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, you see, before we can wander outward into the cold and distant reaches of the solar system, before we speak of planets and moons and the fragile edges where the sun's influence begins to loosen its grip, we must first sit for a moment with the star itself. The sun is not just another object at the center of the story. It is the story's reason for being the quiet architect of everything that follows. And I suppose when you really allow that to sink in, it becomes almost overwhelming. Nearly all of the mass of the solar system, more than 99% of it, is gathered into this single, luminous sphere. Hanging there, calmly, it dominates not through violence or noise, but through gravity, a deep, patient pull that shapes every orbit and every path. You might imagine the solar system as a vast dance floor, planets drifting in graceful arcs, comets arriving late from the shadows, asteroids murmuring between worlds. And at the center, the sun does not move much at all. It simply exists, and that existence is enough to choreograph the entire performance. And yet, the sun is not static. It is alive with motion, with nuclear fire, with pressures so intense that matter itself behaves in ways we never experience on Earth. In its core, hydrogen is fused into helium, releasing energy that takes a long and winding journey outward. That energy does not rush. It can take hundreds of thousands of years to escape the dense interior before finally emerging as light. And when it does, well, it travels across space at the ultimate speed limit of the universe, reaching Earth in just over 8 minutes. 8 minutes. That's all that separates us from the furnace that makes life possible. If the sun were to vanish, which it will not, we would continue living briefly, unaware, until the light simply stopped arriving. And I suppose that idea alone tells you something profound about how dependent we are on a star we rarely think about. The sun's influence is not limited to light and warmth. It extends outward in a constant stream of charged particles known as the solar wind. You cannot see it. You cannot feel it, but it is always there, flowing past Earth, brushing against our magnetic field, shaping the space around every planet. Like breath from a living being, the sun exhales continuously, filling the solar system with motion and energy. This wind creates a vast bubble in space, pushing back against the material between the stars, and it is this invisible breath that helps define how far the sun truly reaches gravity, though is the sun's most powerful expression. Without it, there would be no stable orbits, no predictable seasons, no long-term calm in which life could slowly evolve. Every planet follows a path carved by the sun's mass. Even worlds unimaginably far away feel that pull. And that's the thing. Gravity does not fade suddenly. It weakens gently, slowly, across enormous distances. This is why the idea of an edge to the solar system is so elusive. There is no point where gravity switches off. It simply becomes less persuasive, like a voice growing quieter as you walk away. As we travel farther from the sun, its light dims, its warmth thins, and the solar wind begins to lose its strength. The inner planets live in a region dominated by solar fire and energy. But beyond them, beyond the giants wrapped in gas and ice, the sun's control becomes more subtle. Out there, the environment is shaped by a balance between what the sun gives and what interstellar space takes away. And this gradual weakening is crucial. It is part of how scientists attempt to define the outer reaches of our system, not by distance alone, but by influence. And perhaps what is most humbling is that we have never seen this structure from the outside. We infer it, we model it, we send machines outward and listen patiently for their faint replies. But no human eyes have ever looked back and seen the solar system as a whole. There is no photograph of our home suspended in space like a finished sculpture. Instead, we build the picture piece by piece, measurement by measurement. It is an act of trust in physics, in mathematics, in our understanding of nature. And I suppose that says something rather hopeful about science. It works, even when we cannot see the full picture. The sun also teaches us something about time. It has been shining for billions of years and will continue long after human stories have faded. Its stability is not eternal, but it is reliable on scales that matter to us, that constancy allowed planets to cool, oceans to form, and chemistry to become biology. Without the sun's steady output, Earth would be either frozen or scorched. The narrow range in which life exists is not accidental. It is a delicate agreement between distance, energy, and time. And when you think about that, it feels almost miraculous. Yet, the sun does not rule alone. It shares its dominion with motion, with angular momentum inherited from the cloud that formed it. The planets are not simply captured. They are the remnants of the same rotating disk that gave birth to the sun itself. And so, in a very real sense, every world out there is a sibling, formed from the same ancient material. The sun is the heart, yes, but it is also part of a family bound together by origin as much as by gravity. As we move outward, the sun's role subtly changes. It becomes less a source of warmth and more a distant reference point. Shadows grow longer, temperatures fall dramatically, the physics of atmospheres and surfaces shifts, and this is where the solar system begins to reveal its diversity. Worlds shaped not just by their composition, but by how strongly they still feel the sun's presence. And that gradual transition is the key to understanding everything that comes next. Because once we leave the immediate neighborhood of the sun, we encounter planets that respond to it in very different ways. Some are scorched, some are wrapped in thick atmospheres, some hover at just the right distance for liquid water to persist. And each of these worlds tells a different story about what happens when solar energy meets matter under varying conditions. So, perhaps, as we gently drift away from the sun's blazing heart, carried outward by curiosity rather than propulsion, it is time to begin noticing how these differences emerge, how rocky worlds close to the sun are sculpted by heat and radiation, how proximity alone can determine whether a planet becomes a furnace, a haven, or a frozen desert. And that, is where our journey naturally leads next into the realm of the inner rocky planets, standing closest to the fire, bearing the clearest marks of the sun's relentless influence. And so, as we drift inward rather than outward for a moment, closer to that blazing source, we arrive naturally at the small, dense worlds forged in heat and collision. The rocky planets are the sun's nearest companions. And you see, they are not simply scaled-down versions of one another. They are profoundly different answers to the same question. What happens when stone and metal are placed near a star? The first of these worlds moves so close to the sun that it seems almost reckless. Mercury races along its orbit, locked in a strange rhythm of motion and rotation. One side faces the sun for long stretches, baking beneath an unfiltered glare, while the other is left to freeze in prolonged darkness. And this is why Mercury holds the record for the most extreme temperature range of any planet. In the daylight, the surface becomes hot enough to melt lead. In the night, temperatures plunge so low that even gases can freeze solid. And that's the thing. There is almost no atmosphere to soften these extremes, no blanket of air to carry heat around the planet. Mercury is a world stripped down to essentials: rock, metal, gravity, and sunlight. Standing on Mercury, if such a thing were possible, the sun would dominate the sky. It would appear enormous, harsh, unforgiving. Shadows would be sharp and black, and time itself would feel strange. Days would last longer than years. And I suppose Mercury teaches us our first lesson about proximity. Being close to the sun does not mean being alive or vibrant. It can mean being eroded, exhausted, slowly sculpted by radiation and impact until only the fundamentals remain. Moving outward, just a little farther from the sun, we encounter a planet that appears at first glance to be Earth's twin. Venus is similar in size, similar in mass, similar in composition. And yet it could not be more different. This is where the story becomes quietly unsettling. Venus possesses the strongest greenhouse effect ever observed, a runaway process that transformed what might once have been a temperate world into a furnace. Its thick atmosphere, rich in carbon dioxide, traps heat with astonishing efficiency. Surface temperatures are hot enough to melt metals, not just during the day, but everywhere, all the time. And that's the unsettling part. The sun does not shine dramatically brighter on Venus than it does on Earth. The difference in distance is modest, and yet the outcome is catastrophic. This tells us something deeply important. Climate is not just about how much energy a planet receives, but how that energy is managed. Venus's clouds reflect sunlight, but once heat enters the atmosphere, it cannot escape. The planet breathes slowly, its dense air pressing down with a force that would crush a human instantly. Venus reminds us that similarity in beginnings does not guarantee similarity in endings. Perhaps it once had oceans, perhaps it once had conditions not unlike our own, but small changes, amplified over time, pushed it beyond a threshold. From that point on, there was no going back. And I suppose, when we think about our own world, that lesson lingers quietly in the background. Then there is Earth. And it feels almost strange to speak of it as just another rocky planet. Because to us, it is everything Earth occupies a narrow region around the sun, known as the zone where liquid water can exist on the surface. Not too close, not too far. This delicate positioning allows oceans to persist, clouds to form, and weather to cycle endlessly. Water flows, freezes, evaporates, and returns. And in that movement, chemistry becomes biology. Earth's atmosphere is thin compared to Venus, yet thick enough to protect and regulate. It holds heat, but not too much. It shields us from radiation. It allows sound to travel and pressure to stabilize. And perhaps most remarkably, It exists in a state of balance, maintained not by design, but by feedbacks, oceans absorbing carbon, rocks locking it away, life itself reshaping the air over vast spans of time. And you know, when you look at Earth from space, it does not shout its importance. It is a small blue world, fragile, luminous, suspended in darkness. Its habitability is not guaranteed forever. It is a moment in a long story, a chapter made possible by distance, composition, and time working together in just the right way. Beyond Earth lies Mars, a planet that feels like a memory. Mars is smaller, colder, more distant, but it carries scars that speak of a different past, carved valleys, dried riverbeds, mineral deposits formed in water. These are not ambiguous hints. They are geological sentences written clearly across the surface. Mars once had flowing rivers, perhaps even vast oceans, and yet today it is dry, cold, and thinly blanketed by air. Mars lost much of its atmosphere long ago. Its gravity is weaker, its magnetic field faded, and without those protections the solar wind slowly stripped away its gases. Water escaped or froze underground. The planet transitioned from active to quiet. And this transformation did not happen overnight. It unfolded over immense stretches of time. And that's the thing. Mars is not dead. It is dormant. It preserves its history, like a museum under an open sky. When we explore Mars with robots, we are not just searching for life. We are searching for context. We are asking how planets change, how environments collapse, how thin the margin can be between living world and barren desert. Mars shows us that habitability is not permanent. It must be maintained by a complex interplay of forces. Taken together, Mercury, Venus, Earth, and Mars reveal something subtle and profound. The rocky planets occupy only a tiny fraction of the solar system's vastness. Most of the space, most of the mass beyond the sun itself belongs to other kinds of worlds, but these inner planets are where the sun's influence is most intense, where heat and radiation and gravity shape solid surfaces directly, and perhaps that is why they feel so personal. They are worlds you can imagine standing on worlds with horizons, with ground beneath your feet. They respond dramatically to distance, to atmosphere, to time. Small shifts lead to enormous consequences, and I suppose that makes them mirrors. In studying them, we study possible versions of ourselves as we begin to move outward again, leaving Mars behind. The density of material changes. The sun's heat weakens further. Solid worlds give way to fragments, leftovers from planet formation itself. A region where gravity never quite allowed a planet to fully assemble. Countless rocky bodies orbiting quietly, spaced far apart, remnants of a time when the solar system was still deciding what it would become. And that, you see, is where our journey carries us next, into the vast, misunderstood realm of the asteroid belt, a place shaped as much by absence as by presence. Into the vast, misunderstood realm of the asteroid belt, a place shaped as much by absence as by presence. And you see, when people imagine this region, they often picture chaos, a dense minefield of tumbling rocks, crowded and dangerous, something like a cosmic demolition zone. But that image, though vivid, is almost entirely wrong. The truth is quieter, emptier, and in many ways far more poetic. The asteroid belt lies between Mars and Jupiter, occupying a broad ring of space where a planet never quite came to be, and perhaps that is the most important thing to understand right away. This region is not debris from a shattered world, it is the remains of one that never finished forming. Countless rocky bodies orbit the sun here, each following its own lonely path, separated by enormous distances. If you were to stand on one asteroid and look toward the next, you would see nothing but blackness. Most of the time, you would not even know you were inside a belt at all. And that emptiness tells a story. During the early days of the solar system, when dust and rock were colliding and clumping together, this region had all the ingredients needed to build a planet. But something intervened. Something massive. Something disruptive. Jupiter. The giant planet's gravity stirred this region relentlessly, tugging, twisting, accelerating objects just enough to prevent them from settling into a single world. Instead of forming a planet, the material was kept in motion, locked into countless individual orbits, and so the asteroid belt became a fossil record of planetary formation, frozen in time. Each asteroid is a fragment of that ancient process. Some are small, no bigger than a house. Others stretch for hundreds of kilometers, large enough to be spherical under their own gravity. They vary wildly in composition. Some are metallic, rich in iron and nickel. Others are rocky or carbon-rich, dark and primitive, carrying the chemistry of the early solar system almost unchanged. And that's the remarkable thing. These objects are time capsules. They preserve material from the moment the planets were born. When spacecraft visit asteroids, they are not just exploring space. They are studying history. The surfaces of many asteroids have remained relatively untouched for billions of years. No erosion by wind, no flowing water, no tectonic recycling. What you see is what was left behind when the solar system settled into its current form. And I suppose that gives the asteroid belt a strange dignity. It is quiet, yes, but it remembers everything. Despite its emptiness, the asteroid belt plays an outsized role in shaping the inner solar system. Some asteroids follow orbits that are gently nudged over time by gravitational interactions, particularly with Jupiter. These nudges can alter paths slowly, subtly, until an asteroid finds itself crossing the orbit of Mars or even Earth. And this is where asteroids shift from historical artifacts to potential hazards. Earth's long history of impacts is written into its surface, though many of the scars have been softened or erased by erosion and plate tectonics. Still, the record remains in craters, in mass extinctions, in layers of sediment rich in extraterrestrial material. These collisions are not random acts of violence. They are the natural consequence of a dynamic system still slowly evolving. And that's the thing. The solar system is not finished. It is calm compared to its youth, but it is not static. Yet Jupiter's role is not purely destructive. Its immense gravity also acts as a shield. By capturing or redirecting many potential impactors, Jupiter reduces the number of large bodies that reach the inner planets. Without it, Earth might experience far more frequent catastrophic impacts. And so Jupiter is both architect and guardian, shaping the asteroid belt, while simultaneously protecting the worlds closer to the Sun. This dual role is one of the quiet balances that make our solar system what it is. The asteroid belt also challenges our intuition about space. When we imagine it as crowded, we reveal how difficult it is to grasp scale. The distances involved are vast. Each asteroid is separated by millions of kilometers. Space is mostly nothing. And perhaps this is one of the deeper lessons of astronomy. The universe feels full in our minds, but it is dominated by emptiness. And within that emptiness, structure emerges not through density, but through gravity and motion. Some asteroids are not solitary. They have moons, tiny companions orbiting slowly, held by weak gravity. Others spin rapidly, shaped like elongated potatoes or loose piles of rubble barely held together. These rubble piles are especially fascinating. They are not solid rocks, but collections of fragments bound by gravity alone. A gentle push could reshape them, and yet they persist, orbit after orbit, century after century. Occasionally, an asteroid is struck by another. The collision sends debris drifting away, forming families of objects with shared orbits and compositions. These families allow scientists to reconstruct ancient impacts long after they occurred, like forensic evidence scattered across space. They tell us about violence in the early solar system and the processes that continue quietly, even now. And then there are the near-Earth asteroids, objects whose paths bring them close to our world. Their study is both scientific and practical. We track them, model their orbits, assess their risks, not out of fear, but out of responsibility. Understanding these objects gives us the ability to anticipate and perhaps one day prevent disaster. And I suppose that speaks to a broader theme. Science is not just curiosity, it is foresight. But beyond danger, asteroids also represent opportunity. They are rich in resources, water locked in minerals, metals formed in ancient stellar explosions. In the distant future, they may become stepping stones for exploration or sources of material for building beyond Earth. And in that sense, the asteroid belt is not just a relic of the past, it is a potential bridge to the future. What fascinates me most, though, is how this region connects the inner and outer solar system. It marks a transition, not just in distance, but in character. Inside, we have solid planets with defined surfaces. Beyond, the solar system begins to change dramatically. Worlds grow larger, atmospheres thicken, gravity deepens. The asteroid belt is the threshold, where rocky worlds give way to giants. As we drift through this region, we are moving out of the sun's most familiar domain. The warmth fades, the light weakens, and yet, the gravitational complexity increases. Ahead lies a planet so massive that it reshaped the entire architecture of the solar system. A world whose storms dwarf Earth, whose magnetic field dominates space itself, and whose influence can be felt even here among these scattered remnants. And so, as the asteroids slowly recede behind us, their ancient fragments continuing their silent circuits around the sun, our attention is drawn outward toward that immense presence, waiting just beyond the belt, a gas giant that did not merely form within the solar system, but helped decide what the solar system would become. Waiting just beyond the belt, a gas giant that did not merely form within the solar system, but helped decide what the solar system would become. And as we drift closer to that immense presence, you begin to feel it even before you see it. The gravity thickens. Space itself seems to lean inward, and then, slowly, Jupiter fills the sky. Jupiter is not simply large, it is dominant. It carries more mass than all the other planets combined, excluding the sun itself. And you see, when something holds that much material, it stops being just another planet and starts behaving like a system within a system. Its gravity reaches far, shaping orbits, bending trajectories, influencing regions of space that lie millions of kilometers away. The asteroid belt we just passed through still feels Jupiter's pull, and so do comets arriving from the deep cold beyond. One of Jupiter's most astonishing features is its magnetic field, the strongest of any planet in the solar system. By far, it is so powerful that it carves out a vast magnetic bubble around the planet, trapping charged particles and accelerating them to immense energies. If you could see radio waves with your eyes, Jupiter would glow like a lighthouse shouting into space. And this magnetic realm is not quiet. It crackles with radiation, belts of particles whipping around the planet at incredible speeds. This magnetic power is not just a curiosity. It tells us something about Jupiter's interior. Deep beneath its swirling clouds lies a core region under pressures so extreme that hydrogen behaves like a metal, conducting electricity, generating magnetism on a planetary scale. And that's the thing. Jupiter reveals physics that cannot exist naturally on Earth. It is a laboratory where matter enters unfamiliar states, where equations leave the page and become reality. Then there is Jupiter's role as guardian. The same gravity that prevented a planet from forming in the asteroid belt also intercepts countless objects that might otherwise wander inward. Many comets and asteroids are captured, deflected, or absorbed by Jupiter long before they can threaten the inner planets. In this way, Jupiter acts as a cosmic shield, not perfect, not absolute, but profoundly influential. Earth's long stability may owe much to this distant giant, standing watch far beyond Mars. And yet, Jupiter is not gentle. Its storms are colossal. Its atmosphere churns with energy on a scale that dwarfs our planet. The Great Red Spot, a storm larger than Earth itself, has been raging for centuries. Its persistence reminds us that on Jupiter, weather is not a passing condition. It is a structural feature. Winds scream at hundreds of kilometers per hour. Clouds stack in layers colored by chemistry and light. And through it all, the planet radiates more energy than it receives from the sun. Still cooling, still contracting, still alive with internal heat. As we pull back slightly and let Jupiter settle into context, another giant waits nearby. Saturn appears softer at first glance, less massive, less intense. But that first impression fades quickly, because Saturn holds one of the most striking structures in the solar system: its rings. The rings of Saturn are not solid bands. They are countless particles, ranging from grains of ice to chunks as large as mountains. Each piece follows its own orbit, together forming an intricate, delicate disk encircling the planet like a frozen echo of formation. And you see, these rings should not last forever. Gravitational interactions slowly disperse them. Radiation darkens the ice. Their existence suggests either renewal or youth. And that mystery lingers quietly. Every time we look, Saturn's gravity shapes these rings with precision. Gaps appear where moons orbit, shepherding particles into place, maintaining order within apparent chaos. It is a dynamic system, a conversation between gravity and motion. And perhaps that is why Saturn feels so poetic. It is both massive and graceful, powerful yet fragile in appearance. Like Jupiter, Saturn radiates internal heat. It too is a world of storms and winds, though more subdued in color. Its atmosphere flows in bands. Its interior hides layers of exotic matter, and beneath it all, gravity again plays the leading role, holding together moons, rings, and magnetism in a complex, evolving dance. Then, far beyond Saturn, the nature of the giants begins to change. The sun is dimmer here. The cold deepens, and the planets themselves reflect that shift. Uranus arrives almost shyly, tilted dramatically on its side as if knocked over long ago and never bothered to stand back up. Its axis of rotation lies nearly in the plane of its orbit, and that simple fact transforms everything. On Uranus, seasons are extreme and strange. Each pole experiences decades of sunlight followed by decades of darkness. The planet rolls around the sun rather than spinning upright, and this orientation affects its atmosphere, its magnetosphere, its internal dynamics. Winds still blow, clouds still move, but they do so under a rhythm unlike anything closer to the sun. Uranus is an ice giant, not a gas giant like Jupiter and Saturn. Its interior contains large amounts of water, ammonia and methane under immense pressure, forming hot, dense fluids rather than familiar states of matter. Its blue color comes from methane absorbing red light, leaving behind that cold, serene hue. And perhaps that color reflects the planet's personality: quiet, distant, subtle. But no less complex, Uranus also possesses rings, thin, dark, hard to see, and a magnetic field oddly tilted and offset from the planet's center. This misalignment creates a magnetosphere that wobbles and twists as the planet rotates, producing an ever-changing interaction with the solar wind. Even here, physics refuses to be simple, and beyond Uranus lies Neptune, the last of the giant planets, and perhaps the most dynamic despite its distance. Neptune receives so little sunlight that noon there is dimmer than twilight on Earth. And yet, it hosts the fastest winds ever measured in the solar system, supersonic gusts tearing through its atmosphere, driven not by solar heat, but by internal energy. Neptune is proof that distance from the sun does not mean inactivity. Neptune's storms form and vanish. Its deep blue atmosphere hides layers of complexity. Its gravity shapes a family of moons. And like the other giants, it radiates more heat than it receives, suggesting a warm, restless interior still cooling after billions of years. And that's the remarkable thing. These outer worlds are not frozen relics. They are active, evolving systems. Taken together, the gas and ice giants redefine our sense of scale and importance. They contain most of the planetary mass after the sun. They dominate the architecture of the solar system. Their gravity sculpts paths. Their magnetism fills space. Their presence determines what can exist where. And yet, none of them are places where we could ever stand. They have no solid surfaces, no familiar ground. Instead, their true richness lies in what orbits them, because around these giants circle dozens of moons, worlds in their own right, some larger than planets, some hiding oceans beneath ice, some wrapped in thick atmospheres, some shaped by tidal forces into volcanic furnaces. And you see, it is here, in the shadows of these giants, that the solar system begins to reveal its most surprising possibilities. Because while the planets themselves may be hostile, their moons offer environments shaped by gravity rather than sunlight, heated from within rather than from above worlds, where chemistry and energy combine in unexpected ways. And as we allow our attention to drift away from the giants themselves, drawn instead toward the countless companions moving through their gravitational embrace, we begin to realize that the search for meaning and perhaps even life does not stop with planets. It expands outward into the strange and captivating realm of moons waiting to be understood. Into the strange and captivating realm of moons waiting to be understood. And you see, once you truly accept that planets are not the only worlds worth visiting, the solar system suddenly becomes far richer, more intimate, more surprising. Because moons are not just companions, they are laboratories, they are storytellers. And in some cases, they may be among the most promising places to search for life beyond Earth. Orbiting the giant planets are dozens upon dozens of these worlds, each shaped not only by the sun's distant light, but by the relentless pull of their parent planet. Gravity stretches them, squeezes them, kneads them like soft clay, and that constant flexing generates heat. Heat that does not come from sunlight, but from motion itself. This is tidal heating, and it changes everything. Consider Europa, a moon of Jupiter, smooth and pale, its surface etched with long, dark cracks like fractures in ice, and that is precisely what they are. Europa is wrapped in a thick shell of frozen water, but beneath that shell, hidden from view, lies a global ocean. An ocean kept liquid not by the sun, but by Jupiter's immense gravitational grip. As Europa moves along its orbit, Jupiter's pull stretches and compresses the moon again and again, generating internal heat, and that heat prevents the ocean from freezing solid. This ocean is not small. It may contain more water than all of Earth's oceans combined, and it is in contact with a rocky sea floor. That detail matters, because where water meets rock, chemistry becomes interesting. Energy gradients form, nutrients circulate, and on Earth, those conditions gave rise to life at the bottom of our own oceans, long before sunlight ever touched living cells. And so, Europa quietly challenges our assumptions. It suggests that life does not require a warm surface or a nearby star. It requires energy, chemistry, and time. And yet, Europa is not alone. Jupiter's system is crowded with remarkable moons. Io is torn apart by tidal forces, its surface constantly reshaped by volcanic eruptions. Lava flows across it in brilliant colors, making it the most volcanically active body in the solar system. Ganymede, the largest moon of all, is bigger than Mercury itself. It has its own magnetic field, a rarity among moons, and beneath its surface, there may also be layers of liquid water stacked between ice and rock. Each of these moons exists within Jupiter's powerful radiation belts, a hostile environment for unprotected life. Yet beneath their surfaces, shielded by ice and rock, conditions may be surprisingly gentle. And that contrast is profound. Violence above, calm below. It reminds us that habitability is not always obvious. It can hide beneath extremes. Then there is Saturn, and its most famous moon, Titan. Titan is wrapped in a thick atmosphere rich in nitrogen with clouds and weather and seasons. It is the only moon in the solar system with a substantial atmosphere. And on its surface rivers flow, but not with water, with liquid methane and ethane. These hydrocarbons carve channels, fill lakes, and fall as rain from orange-tinted skies. Titan is cold, unimaginably cold, and yet it is chemically rich. Sunlight and radiation drive complex reactions in its atmosphere, producing organic molecules that drift downward and settle on the surface. This chemistry is not life, but it is prebiotic. It resembles the early stages of what might have occurred on Earth long before biology took hold. And I suppose that makes Titan feel like a frozen echo of our own beginnings. a reminder that the ingredients for life may be widespread, even if the outcomes are rare. Beneath Titan's icy crust, there may also be an ocean of liquid water mixed with ammonia. Again hidden, again warmed from within, again protected from the harshness of space. And so Saturn too hosts worlds that blur the line between moon and planet, between dead and potentially alive. As we move outward to Uranus and Neptune, the moons grow stranger still. These are quieter systems, more distant, more subtle. Yet even here, tidal forces and internal heating play their roles. Some moons show signs of resurfacing. Others may harbor subsurface oceans kept liquid by antifreeze-like compounds. And although sunlight is faint, the internal engines continue to run. What unites these moons is not size or location, but process. They are shaped by interaction. Their histories are written by gravity and motion, rather than distance from the sun. And that realization expands our understanding of where life might exist. It frees us from the idea that only Earth-like planets in narrow zones can host biology. Instead, it opens the door to hidden oceans and internal warmth scattered throughout the solar system. And perhaps that is one of the most humbling lessons. Moons were once considered secondary objects of lesser importance, but now they stand at the forefront of exploration. They may hold answers that planets cannot. And I suppose that says something about perspective. What we overlook at first often turns out to be essential. These moons also deepen our emotional connection to the solar system. They are worlds you can imagine landing on, standing beside methane lakes, watching Saturn hang massive and luminous in the sky, or drilling through ice to release water untouched for billions of years. They invite curiosity, not just scientifically, but viscerally. And yet, for all their promise, these moons are still bound tightly to their planets. Their fates are intertwined, their environments shaped by gravitational embrace. As we continue outward, leaving these moon-rich systems behind, the architecture of the solar system begins to thin. The number of large bodies decreases. The distances grow. The light fades further. Ahead lies a vast disk of icy remnants beyond the last giant planet, a region populated by small cold worlds orbiting quietly at the edge of sunlight, a place where Pluto resides not as an anomaly, but as one among many. And so, as the moons slowly recede into the darkness behind us, our attention drifts outward once more toward the Kuiper Belt, a distant frontier where the solar system begins to loosen its grip, and the long, slow journey toward interstellar space truly begins. Toward the Kuiper Belt, a distant frontier where the solar system begins to loosen its grip and the long, slow journey toward interstellar space truly begins. And as we cross the orbit of Neptune, something subtle but profound happens. The sun is still there, of course, still shining, still pulling, but its presence feels thinner now. Its warmth is no longer something you feel. Even light itself seems hesitant. Out here, the solar system changes character. It becomes quieter, colder, more spacious. And you see, this is where the Kuiper Belt begins. The Kuiper Belt is not a sharp boundary. It does not announce itself with a sudden shift. Instead, it emerges gradually, a vast disk of icy bodies extending far beyond Neptune's orbit, countless objects moving slowly in the dim outskirts of sunlight, each one a frozen remnant from the early days of planetary formation. And perhaps the most important thing to understand is that this region is immense, far wider and far thicker than the asteroid belt we passed earlier. Where the asteroid belt is dominated by rock and metal, the Kuiper Belt is a realm of ice, water, ice, methane, ice, ammonia. Ice, substances that near the sun would vaporize instantly, but here remain locked in solid form. The temperature is so low that molecular motion itself seems to slow. Objects here exist in a state of deep freeze, preserved almost timeless. And that preservation is what makes the Kuiper Belt so valuable scientifically. These bodies are leftovers. They are the building blocks that never became planets. When the giant planets formed and migrated early in the solar system's history, they scattered material outward. Some objects were flung far away. Others were trapped into stable orbits beyond Neptune, and over billions of years, they have remained largely unchanged, orbiting. Quietly in the dark, among these objects is Pluto, and when Pluto was first discovered, it felt like an oddity, a lonely outpost at the edge of the known planetary system. But now we understand that Pluto is not alone. It is one of the largest members of a vast population. Pluto is a representative of the Kuiper Belt, not an exception, and that realization transformed our understanding of the outer solar system. Pluto itself is a complex world. It has mountains made of water ice, plains of frozen nitrogen glaciers that flow slowly over geological time. Its thin atmosphere expands and collapses as it moves along its elongated orbit, and beneath its surface there may even be a subsurface ocean kept liquid by internal heat. And that's the thing, even here. Even this far from the sun, worlds are not necessarily dead. They can still be active, evolving, surprising. But Pluto is just the beginning. The Kuiper Belt contains thousands of known objects and likely millions more. Some are small and irregular. Others are large enough to be spherical under their own gravity. Many have unusual orbits, tilted and stretched compared to the neat planes of the inner planets. These eccentric paths tell a story of ancient gravitational disturbances, a time when the giant planets shifted position, reshaping the architecture of the entire system. And then there is the darkness. Sunlight out here is more than 1,000 times weaker than it is on Earth. Noon in the Kuiper Belt would feel like perpetual twilight. Shadows would be soft and indistinct. The sun itself would appear as a brilliant star rather than a blazing disk. And yet, despite this dimness, these objects continue their slow circuits year after year. Millennium after millennium, time behaves differently here. Or perhaps our perception of time does. Orbits take centuries. Even millennia to complete motion is unhurried. Change is subtle, and I suppose that invites reflection. The Kuiper Belt is a place where patience reigns, where processes unfold on timescales far beyond human experience. Many comets begin their journeys here. Disturbed by gravitational interactions, they are nudged inward toward the sun. As they approach warmth for the first time in billions of years, their ices vaporize, creating glowing comas and sweeping tails. And for a brief moment, these ancient objects become visible reminders of the solar system's distant edges. Comets are messengers, carrying material from the Kuiper Belt into the inner worlds. They connect the outskirts to the center. They remind us that the solar system is a single integrated structure, not a collection of isolated regions. And that's something easy to forget when distances grow so large. But gravity does not forget, neither does momentum or history. The Kuiper Belt exists because of everything that happened closer in, because Jupiter grew massive, because Neptune migrated, because collisions and resonances shaped what survived. And so this region is not separate. It is the outcome of everything that came. Before, the Kuiper Belt is also thick, not a thin ring, but a broad disk extending above and below the plane of the planets. Objects here are scattered in 3 dimensions, giving the region depth and complexity. And beyond its main population lies an even more diffuse region where objects are barely bound to the sun, their orbits stretched into long, slow arcs. As we move through this region in our imagination, the sense of being at the edge grows stronger. The planets are far behind. The sun is distant, and yet we are still very much within the solar system. The sun's gravity still holds sway. Objects here are still members of its family. And that raises an intriguing question. Where does the solar system truly end? Is it where the planets stop? Is it where icy bodies thin out? Is it where the sun's gravity finally loses its grip? The Kuiper Belt forces us to confront the fact that boundaries in space are rarely clear. They are gradients, transitions, zones of overlap rather than lines on a map. And perhaps that is why the Kuiper Belt feels so philosophical. It exists in between. It is neither the familiar inner system nor the truly interstellar. It is a liminal space. A threshold, and thresholds are always interesting places. As we continue outward, the objects become fewer. The darkness deepens. Further still lie scattered disk objects on wild orbits that carry them far from the sun before returning slowly like deep breaths. And beyond even them lies a population so distant and diffuse that we have never seen it directly. But before we reach that realm, the Kuiper Belt offers one final lesson: scale. The solar system is far larger than the planetary diagrams we grew up with. The distance from the sun to Neptune feels vast, yet the Kuiper Belt extends many times farther. And still, this is not the end. It is only another layer. And so, as the last of the familiar Kuiper Belt objects drift behind us, their frozen surfaces reflecting faint starlight, we find ourselves approaching a region where worlds grow stranger still, where classification becomes difficult, where names like planet and moon begin to lose their clarity. Ahead lies a population of distant bodies, once thought to be planets, then reconsidered, then reimagined worlds like Pluto, Eris, and many others still unnamed objects that occupy the transitional zone between the Kuiper Belt and the deeper darkness beyond. And it is here, in this realm of dwarf planets and remote wanderers, that our journey continues outward toward the fading influence of the sun and the quiet approach of true cosmic isolation. Toward the fading influence of the sun and the quiet approach of true cosmic isolation. And yet, before the solar system dissolves into that near infinite darkness, it passes through a region that challenges our need for neat categories, a place where objects are too large to be simple debris and too small or too unconventional to fit our old definition of planets. This is the realm of dwarf planets and distant wanderers. And you see, this region asks us not just to observe, but to reconsider. For a long time, Pluto stood alone in our imagination. Discovered in the early 20th century, it was welcomed as the ninth planet, a small, lonely world at the edge of the sun's domain. It occupied textbooks and memory with quiet dignity, and perhaps that is why its reclassification stirred such emotion, because Pluto was not just an object. It was a story we told ourselves about order and completion, but as our instruments sharpened and our surveys widened, Pluto began to feel less solitary. Objects with similar sizes, similar compositions, similar orbits started to appear. They did not fit the simple picture of 8 planets and a distant outlier. Instead, they revealed a population. A family Pluto was not the odd one out. It was the first known member of something much larger. Pluto's orbit itself hints at this complexity. It is highly eccentric, stretched far from the sun and then drawn inward again. It is tilted steeply compared to the plane of the planets, and during part of its long year, Pluto is actually closer to the sun than Neptune. These characteristics once seemed strange for a planet, but in the context of the Kuiper Belt and beyond, they make perfect sense. Pluto behaves like a resident of a transitional zone shaped by ancient gravitational interactions. Pluto is also surprisingly dynamic. Its surface hosts glaciers of nitrogen ice that flow slowly over time. Its atmosphere appears and disappears as it moves closer to and farther from the sun. It has mountains made of water, ice harder than rock at such low temperatures, and beneath its frozen crust there may be a subsurface ocean kept warm by radioactive decay and perhaps ancient tidal heating. And that's the thing. Even small distant worlds can be complex, alive with processes unfolding at a pace we are only beginning to appreciate. Then there is Eris, a world discovered in the early 21st century that is comparable in size to Pluto and possibly more massive. Its discovery was one of the key moments that forced astronomers to rethink the definition of a planet. Eris follows a wildly elongated orbit, carrying it far beyond the main Kuiper Belt into regions where sunlight is little more than a whisper. For much of its year, Eris is unimaginably cold, colder even than Pluto. Its surface is coated with frozen gases that would boil away instantly nearer the sun. Eris represents the extreme end of this population. Objects that spend most of their existence in deep freeze, only briefly approaching regions where solar energy has any noticeable effect. And yet, even these worlds are not inert. They respond to the sun, however faintly. Their surfaces evolve. Their ices shift phase. Their orbits change slowly over time under the influence of distant giants. These dwarf planets are not isolated. They belong to a broader collection of objects with diverse and often eccentric paths. Some are part of the scattered disk, a region where objects have been flung onto elongated orbits by interactions with Neptune. These bodies may travel hundreds of astronomical units away before slowly returning. Their orbits are like long breaths in and out of the solar system, carrying them between light and darkness. Many of these objects have not yet been named. They are known only by catalog numbers and provisional designations. Each one represents a discovery waiting to be understood, a point of light moving against the background stars, detected only through patient observation. And I suppose there is something humbling about that. Our solar system still holds countless members. We barely know. The orbits of dwarf planets and distant objects tell a story of migration and chaos. Early in the solar system's history, the giant planets did not sit quietly where we see them today. They moved. They exchanged angular momentum with the surrounding disk, scattering material inward and outward. This period of instability sculpted the outer regions, leaving behind populations with tilted, stretched, and resonant orbits. What we see now is the aftermath, a system that has settled but still carries the memory of its youth. Some dwarf planets travel in resonances with Neptune, locked into gravitational rhythms that keep their orbits stable over billions of years. Pluto itself is part of such a resonance, completing 2 orbits for every 3 of Neptune. This relationship prevents close encounters and maintains long-term stability. It is a subtle, elegant dance choreographed by gravity alone. And yet, not all objects are so neatly constrained. Some wander on paths that suggest influences we do not fully understand. Their orbits cluster in unexpected ways, raising questions about unseen forces or distant massive bodies. Perhaps there are still major players in the outer solar system waiting to be discovered. Or perhaps the solar system's early history was even more complex than we currently imagine. What is clear is that this region marks a profound transition. The neat architecture of planets gives way to a continuum. Sizes blend, categories blur. The difference between a planet, a dwarf planet, and a large Kuiper Belt object becomes less about physical reality and more about human definition. And maybe that is inevitable. Language always lags behind discovery. These distant worlds also challenge our emotional attachment to the idea of planets. Why should size or orbit determine importance? Pluto did not become less interesting when it lost its planetary title. If anything, it became more so, because now it represents an entire class of worlds. And in understanding Pluto, we understand many others. As we move farther out among these objects, the sun continues to fade. Its light is weak, its warmth negligible, yet its gravity still holds. Even here, the sun remains the central anchor, but its dominance feels gentler, more permissive. Objects take longer to complete their orbits. Time stretches further, and the sense of being on the outskirts grows stronger. Some of these distant bodies may be the source of long-period comets. Disturbed by passing stars or galactic tides, they may be nudged inward, beginning journeys that last thousands or even millions of years. These comets carry pristine material from the farthest reaches of the solar system, inward, delivering it briefly to regions of warmth and light. They are messengers from beyond the familiar, and that is perhaps the deeper role of dwarf planets and distant objects. They are intermediaries. They connect the structured inner solar system to the diffuse outer realms. They remind us that the sun's family does not end with the last planet. It thins, gradually fading into populations that blur into the background of the galaxy. As we drift still farther outward, the objects grow fewer and their orbits longer. The Kuiper Belt gives way to even more tenuous populations. The scattered disk stretches into something more spherical, more diffuse. A region only inferred, never directly observed, and beyond that lies a vast halo of icy bodies surrounding the sun on all sides. But before we reach that remote cloud, we must follow the paths of the objects that occasionally return to the sun, blazing briefly before vanishing again. Objects whose journeys span thousands of years, whose appearances are fleeting, whose origins lie in the deep, dark edges we are approaching. And so our attention shifts naturally from distant static worlds to travelers wanderers on long looping orbits. Ahead are comets, ancient icy messengers carrying the memory of the solar system's birth. Their paths will guide us outward and inward, showing us how the farthest reaches remain connected to the center, and through them we begin to sense the true scale of the sun's influence stretching far beyond the last dwarf planet into realms where time and distance lose their familiar meaning. Their paths will guide us outward and inward, showing us how the farthest reaches remain connected to the center, and so, naturally, our attention settles on these travelers, the comets, the wanderers whose journeys stitch together the inner warmth and the outer cold of the solar system. You see, comets are not residents in the way planets are. They are visitors. They spend most of their existence far from the sun, drifting through regions of deep darkness where time moves slowly and temperatures hover just above absolute stillness. For thousands of years, sometimes tens of thousands, they remain unchanged, preserved like cosmic fossils waiting patiently for a brief encounter with light. A single orbit for some comets can last longer than the entirety of human civilization. From the moment they begin their long fall inward to the instant they swing back out into the cold again, millennia may pass, and that alone should give us pause. These objects do not experience the solar system as we do. They witness it across vast spans of time. They remember conditions that predate Earth as we know it. As a comet approaches the sun, something extraordinary happens. The heat awakens it. Ices that have remained solid since the dawn of the solar system begin to sublimate, turning directly from solid to gas. The comet grows a glowing envelope called a coma, a temporary atmosphere that can stretch for thousands of kilometers. And then comes the tail, or rather tails, because comets often grow more than one. And here is one of those quietly beautiful truths. The tail of a comet always points away from the sun. Always. It does not trail behind the comet like smoke behind a train. Instead, it is sculpted by sunlight and solar wind, pushed outward by radiation pressure and streams of charged particles. No matter which direction the comet is traveling, the tail faces away from the sun, like a weather vane responding to an invisible wind. This simple fact reveals something profound about the sun's influence. Even here, even on these ancient wanderers, the sun asserts itself. Not through gravity alone, but through light and plasma. The solar wind reaches far enough to shape comets into luminous messengers, announcing their arrival long before they become visible to the naked eye. The composition of comets is remarkably primitive. They are mixtures of ice dust and organic compounds, materials that have remained largely unchanged since the solar system formed. In that sense, comets are time capsules. They carry within them the chemistry of the early solar nebula. And when they pass close to the sun, they release that material into space, offering us a glimpse of the ingredients that built planets, oceans, and perhaps life itself. Some comets are born in the Kuiper Belt. Their orbits are relatively short, measured in decades or centuries. These short-period comets return again and again, slowly losing material with each passage. Eventually they fade, break apart, or become dormant, leaving behind trails of debris that can create meteor showers on Earth. These showers are gentle reminders that we pass through the ghosts of comets every year, watching fragments burn briefly in our atmosphere, like fleeting sparks. Other comets come from much farther away. Their orbits are vast, elongated arcs that carry them from the deepest outskirts of the solar system into the inner regions, only once in many thousands of years. These long-period comets arrive without warning, appearing suddenly from directions unaligned with the planets. They seem almost random, unpredictable, and yet their paths follow the same laws of gravity as everything else. They are not chaotic, they are simply distant. When a long-period comet appears, it is a rare event. A visitor from a realm we have never seen directly. Its brightness may grow dramatically, its tail stretching across the sky, dominating the night. And then just as suddenly it departs, heading back toward darkness. perhaps never to return, or perhaps to return long after humanity itself has changed beyond recognition. And that's the thing. Comets force us to confront deep time. They remind us that the solar system is not arranged. Around our experience, we are brief witnesses passing through a much longer story. These objects were here long before us and will continue long after. As comets approach the sun, they undergo stress, thermal stress. Jets of gas erupt from their surfaces, creating uneven forces that can alter their rotation, even tear them apart. Some comets split into fragments, others disintegrate entirely, leaving nothing behind but a fading trail. And when that happens, it is not destruction so much as transformation. Their material returns to the solar system, becoming part of the interplanetary dust that drifts between worlds. Comets also carry information across distances. They can deliver water and organic molecules to inner planets. It is possible that long ago comets contributed to Earth's oceans and chemistry, not alone, but as part of a broader exchange between inner and outer regions. And so these wanderers may have played a role in making life possible here. A humbling thought, that our existence may be linked to icy bodies formed far beyond the reach of warmth. The orbits of comets are shaped by gravity, but also by chance. Passing stars, galactic tides, subtle nudges over millions of years can send a comet inward, or fling it away forever. In this way, the solar system is not isolated. It interacts gently with its galactic environment. The space between stars is not empty of influence. It whispers rather than shouts. But over time, those whispers matter. And this brings us to an important realization. The paths of comets reveal the structure of the outer solar system, even where we cannot see it directly. By studying their orbits, their arrival directions, their energies, we infer the existence of distant reservoirs of icy bodies, vast populations too faint and too remote to observe directly, yet real nonetheless. Some comets arrive from regions far beyond the Kuiper Belt, from distances so great that the sun appears as just another star among many. Their journeys begin in a place where the sun's gravity is barely stronger than the pull of the galaxy itself, and when they finally fall inward, they cross a boundary subtle but profound, the point where the sun's influence becomes dominant once more. As we follow these paths outward in our imagination, the solar system begins to feel less like a flat disk and more like a three-dimensional structure, extended and diffuse. Comets do not respect the plane of the planets. They arrive from above, below all directions. Their orbits sketch out a vast spherical domain surrounding the sun, a realm inferred rather than seen. And so comets are not just objects, they are clues. They tell us where material is stored. They tell us how the sun's influence fades gradually, rather than ending abruptly. They show us that the solar system is porous, open to the galaxy, slowly exchanging material across immense timescales. As we drift with them farther outward, the sun's light grows weaker still. The warmth disappears entirely. Space becomes dominated by cold and gravity and long silence. And yet the sun's wind still flows. Out here it is slower, thinner, but still present, carrying the sun's magnetic field far into space. And this is where the next transition begins. Because beyond a certain distance, the solar wind no longer dominates. It meets resistance from the interstellar medium. The diffuse gas and magnetic fields that fill the space between stars push back. And where these two influences meet, a boundary forms. Not a wall, but a region. A frontier, defined not by objects, but by forces. The journeys of comets bring us to the threshold of that boundary. They originate beyond it, pass through it, and return again. They are witnesses to the edge of the sun's breath, and by following them outward, we are naturally led to consider that invisible border, the place where the solar wind slows, where its strength diminishes, where the sun's influence begins to yield to the galaxy. And so, as the last of the cometary paths stretch outward, fading into the darkness, our attention shifts from icy travelers to the environment they move through, to the vast bubble carved by the sun itself. a region defined not by matter but by motion and pressure. Ahead lies the frontier of the solar wind, the boundary where the sun's influence meets the interstellar medium, a place no human has ever visited, but a few silent machines have reached, carrying our questions into the dark. And it is toward that invisible edge that our journey now continues. Toward that invisible edge that our journey now continues. And here, you see, the solar system begins to reveal itself not through planets or comets or solid worlds, but through something far more elusive. A boundary made of motion, a frontier shaped by pressure and energy, rather than rock or ice. This is the realm of the solar wind and the vast bubble it creates around our sun. The sun is not silent. It does not merely shine. It breathes constantly, endlessly. From its outer atmosphere, charged particles stream outward in all directions at tremendous speeds. This outflow is what we call the solar wind, and it fills the space between the planets, flowing past worlds, moons, and comets alike, carrying with it the sun's magnetic field stretched outward into long spiraling arcs. Near Earth, the solar wind is something we experience indirectly. It shapes auroras. It disturbs satellites. It interacts with our magnetic field. But as we move farther from the sun, this wind becomes the dominant feature of space itself. It defines the environment. It determines how particles move, how energy flows, how matter behaves. Over vast distances, the solar wind carves out a gigantic cavity in the surrounding interstellar medium, a protective bubble surrounding the sun and all its planets. This bubble is known as the heliosphere, and it is enormous, extending far beyond the orbit of Neptune, enveloping the Kuiper Belt and dwarf planets, stretching outward into regions where sunlight is barely a presence. Inside the heliosphere, space is shaped. Primarily by the sun outside it, the galaxy begins to assert itself. And the boundary between these two realms is not sharp, it is not fixed. It breathes, it shifts, it responds to changes in the sun's activity and the conditions of the interstellar space through which the solar system moves. As the solar wind travels outward, it gradually slows. It begins fast and energetic near the sun, but loses momentum as it expands and collides with itself and with interstellar particles. Eventually, it reaches a point where it can no longer push back effectively against the pressure of the interstellar medium. This slowing marks the beginning of a transition zone, a region where the sun's breath weakens and the galaxy pushes back. This region is vast and complex. It is not a wall, but a layered boundary filled with turbulence. Magnetic fields twist and fold, particle densities change, shock waves form, and through it all, the solar wind continues to decelerate. This slowing is one of the first signs that we are approaching the true outer edge of the sun's influence. What is remarkable is that this boundary was predicted long before it was ever reached. Mathematical models suggested that the solar wind must eventually be balanced by the pressure of the interstellar medium, that the sun could not dominate space indefinitely, and yet, until relatively recently, this idea remained theoretical, a concept drawn on paper rather than observed. The environment here is unlike anything closer to the sun. Temperatures rise even as energy decreases. The particles slow, but become more chaotic. Magnetic fields strengthen and weaken unpredictably. It is a place of compression and confusion where order gives way to complexity, and I suppose that feels fitting. Boundaries are rarely simple. They are places of change and uncertainty. The solar wind does not simply stop when it slows. It piles up, it thickens, like a traffic jam in space. Particles crowd together, forming a region of increased density and pressure. And within this region, the sun's magnetic field becomes tangled, folded back on itself, stretched thin by the relentless outward flow. At the same time, interstellar space is not empty. The space between stars contains gas dust, cosmic rays, and magnetic fields. As the solar system moves through the galaxy, it plows gently through this medium, creating a kind of wake. And the heliosphere responds to that motion-changing shape, becoming slightly compressed in the direction of travel and elongated behind like the tail of a comet. This means that the solar system is not symmetrical. Its boundary is shaped by motion, by environment, by history. Even here at the edge, the sun is interacting with the larger galaxy, responding to forces far beyond its own making. One of the most subtle and fascinating aspects of this region is the role of cosmic rays, high-energy particles born in distant supernovae and violent galactic events constantly bombard the solar system. The heliosphere acts as a shield deflecting many of these particles, reducing the radiation that reaches the inner planets. As the solar wind weakens near the boundary, this shielding becomes less effective. Cosmic rays penetrate more easily, their numbers increase, and this change marks another quiet signal that the sun's influence is fading. Inside the heliosphere, the sun moderates the cosmic environment. Outside it, the galaxy takes over, and the transition between these two regimes is gradual, nuanced, and dynamic. It is shaped by solar cycles, by long-term changes in stellar activity, by the varying density of the interstellar medium. The boundary of the solar wind is not fixed in place. It moves inward and outward over time. As the sun becomes more active, the solar wind strengthens, pushing the boundary farther out. When the sun quiets, the boundary contracts, and over longer timescales. As the solar system travels through different regions of the galaxy, encountering clouds of varying density, this boundary can shift dramatically, and that realization is quietly profound. The size of our solar system is not constant. It changes. It breathes with the sun and the galaxy. It is a living structure responding to its environment. This region also marks the beginning of true isolation. Communication across it becomes more difficult. Signals weaken. The density of matter drops. Even the familiar hum of solar particles thins. And yet, despite this thinning, the solar wind still carries information. It carries the sun's magnetic signature outward, imprinting its identity onto space far beyond the last planet. For centuries, the edge of the solar system was imagined as a place defined by objects, a final planet, a final orbit. But here, we learn that the true boundary is defined by forces, by pressure balances, by invisible interactions between charged particles and magnetic fields. And perhaps that is more beautiful. It suggests that the universe is not divided by walls, but by gradients, by negotiations between competing influences. The heliosphere is also our cocoon. It is what makes the solar system a relatively calm place. Compared to the harsh radiation environments near some stars or in dense galactic regions, our heliosphere provides shelter. It reduces radiation. It stabilizes conditions. It creates a bubble in which life on Earth has been able to persist. And that brings a sense of intimacy to this vast structure. This enormous invisible bubble stretching billions of kilometers exists quietly around us, protecting us, shaping our cosmic environment. Without it, Earth would be exposed to far higher levels of radiation, and life might have taken a very different path. As we drift farther outward in our imagination, the solar wind grows slower still. Its pressure continues to drop. The turbulence increases. The balance tips gradually toward the interstellar medium, and ahead lies a more definitive boundary, a place where the solar wind finally yields completely. But even now, before reaching that point, we can sense the change. The sun's voice grows quieter. The galaxy's presence grows stronger. The solar system feels less like a self-contained island and more like a region embedded within something larger. And perhaps that is the emotional weight of this chapter. To realize that the sun, though powerful, though central, does not rule forever. Its influence is vast but finite. It fades gradually, giving way to the greater structure of the galaxy. And this fading is not sudden or dramatic. It is slow, almost tender, a gentle relinquishing of dominance. As we approach the outermost reaches of the solar wind, we stand on the threshold of something new. A final boundary where the sun's breath comes to rest, where its magnetic field can no longer push outward, where interstellar space presses back fully. This boundary is known as the heliopause, the place where the solar wind stops being the dominant force, the place where the sun's influence officially ends, and the galaxy begins, and it is here that a few silent messengers built by human hands have ventured, carrying our curiosity farther than any living being ever could. And so, with the solar wind slowing around us, with cosmic rays increasing with magnetic fields, twisting in unfamiliar ways, we move toward that final frontier. The heliopause, a doorway into interstellar space, where the sun's long reach finally releases its hold, and the vastness beyond waits in quiet darkness. Where the sun's long reach finally releases its hold, and the vastness beyond waits in quiet darkness. And here, you see, we arrive at a place that is less a location and more a moment where influence ends, not with a crash or a line, but with a gentle surrender. This is the heliopause, the outermost breath of the sun, the place where its voice, carried on the solar wind, finally falls silent. For billions of years, the sun has been speaking into space, not with sound, of course, but with particles and fields, a steady outward flow shaping everything within its domain. And all along this journey, from the inner planets to the comets and the Kuiper Belt, that voice has been present, guiding motion, setting tone, defining what it means to be inside the solar system. But here, at the heliopause, that changes. The heliopause is the boundary where the solar wind no longer has the strength to push outward against the interstellar medium. Beyond this point, the pressure of the galaxy outweighs the pressure of the sun. The particles streaming from our star slow to a stop. They mingle, they turn back, or they are swept away. And in that balance, the sun's direct influence ends. It is tempting to imagine this boundary as a wall, but it is nothing of the sort. It is a complex, fluctuating surface shaped by motion, turbulence, and time. Magnetic fields twist and reconnect. Particles exchange energy. The environment shifts depending on solar activity and the density of the surrounding interstellar space. And that's the thing. The heliopause is alive in its own subtle way, not static, not fixed, but responsive. Crossing this boundary means entering a fundamentally different environment. Inside the heliosphere, space is dominated by solar particles. Outside it, space belongs to the galaxy. The composition of particles changes. The direction of magnetic fields shifts. Cosmic rays become far more abundant. The sun's magnetic imprint weakens, and suddenly the space around you is no longer solar, it is interstellar. For most of human history, this boundary existed only in equations and imagination. Scientists inferred its existence from theory and indirect observation. But eventually, after decades of silent travel, a human-made object reached it. Voyager 1, a small probe launched in the late 20th century, carrying instruments and a message. It traveled outward, planet by planet, year by year, long after its original mission had ended. And then, quietly, it crossed the heliopause. There was no fanfare, no sudden image, no dramatic signal, just a subtle change in data, a shift in particle density, a reorientation of magnetic fields, a rise in cosmic ray intensity. These were the fingerprints of crossing from one realm into another, and in that moment, Voyager 1 became the first human artifact to leave the heliosphere. That crossing marked the first time anything built by our species entered true interstellar space, not the space between planets, but the space between stars. And I suppose that realization carries a quiet, emotional weight. A machine built by beings on a small rocky world had traveled far enough to leave the protective bubble of its parent star. Beyond the heliopause, the physical conditions are stark. The density of matter is extremely low. Temperatures are difficult to define because particles rarely interact. Magnetic fields stretch across vast distances shaped by the galaxy itself. Radiation levels are higher. The environment is harsher, less forgiving, and yet this is the normal state of space. Most of the universe exists in conditions like these. The heliopause marks the last boundary where the sun offers shelter, where its wind deflects cosmic rays, where its magnetic field provides a degree of protection. For life on Earth, this boundary matters deeply. Without the heliosphere, our planet would be exposed to far greater radiation. The conditions for life would be more hostile. The story of biology might have unfolded very differently. And so the heliopause is not just a scientific curiosity, it is part of the reason we are here. It is an invisible guardian, marking the edge of a safe harbor carved out in a vast and often violent galaxy. Yet even here, the sun is not entirely absent. Its gravity still extends far beyond this boundary, holding distant objects in long, slow orbits. The heliopause marks the end of the sun's plasma influence, but not the end of its gravitational reach. And that distinction is important because it reminds us that boundaries in space are layered, overlapping, defined by different forces. Crossing the heliopause also changes our perspective on the solar system. Inside, we tend to think of the sun as dominant, as central, as defining everything. Outside, it becomes just one star among many. Its light fades. Its particles disperse, its magnetic influence disappears into the background of the Milky Way. And perhaps that is one of the most humbling moments in our journey. To realize that our sun, though essential to us, is not exceptional on cosmic scales. It is one of hundreds of billions of stars, each surrounded by its own sphere of influence, each carving out its own heliosphere or astrosphere in the galactic medium. The heliopause also teaches us about impermanence. The sun will not always have the same influence over time. As it evolves, as it brightens and eventually sheds its outer layers, the size and shape of its heliosphere will change. The boundary will move, the conditions will shift, and long after humanity is gone, this structure will continue to evolve, responding to forces far beyond our control. Beyond the heliopause lies interstellar space, but that space is not empty. It contains gas dust, cosmic rays, and magnetic fields. It is the raw material from which new stars and planets will one day form. In that sense, leaving the heliosphere is not an end. It is a return to the broader galactic environment from which the solar system itself was born. And yet, even now, even having crossed this threshold, our journey outward is far from over. Because while the heliopause marks the end of the sun's wind, it does not mark the end of the sun's family. Far beyond this boundary lie objects still gravitationally bound to the sun, bodies so distant and so faint that we have never seen them directly. These objects form a vast spherical halo surrounding the solar system, extending far beyond the heliopause into regions where the sun's gravity barely holds on. They are the source of the longest period comets. They mark the outermost frontier of the sun's gravitational domain, and they represent the final structure of the solar system itself. This is the Oort cloud, a realm inferred rather than observed, a population of icy bodies spread across distances measured not in millions, but in trillions of kilometers, a structure that blurs the line between solar system and interstellar space. And so, as Voyager 1 continues its silent journey deeper into the galaxy, carrying with it a record of our existence, we find ourselves compelled to follow its path outward beyond the heliopause, beyond the last breath of the sun, toward that distant spherical cloud where the solar system fades almost imperceptibly into the cosmic ocean. Because the story does not end at the heliopause, it simply changes scale. And in that change, we are reminded once again that every boundary in the universe is also a doorway, leading us onward into deeper darkness and deeper understanding, toward that distant spherical cloud where the solar system fades almost imperceptibly into the cosmic ocean. And here, you see, we reach a place that no human eye has ever seen directly, a realm that exists not because we have photographed it, but because the universe behaves in ways that leave traces. This is the Oort cloud. And perhaps more than any other region we have encountered, it exists halfway between certainty and imagination. The Oort cloud is not a disk like the Kuiper Belt. It is not aligned neatly with the plane of the planets. Instead, it surrounds the sun in all directions, forming a vast, diffuse sphere, a halo of icy bodies extending tens of thousands of astronomical units outward, distances so large that light itself takes days to cross them, and that scale alone should give us pause. because here, the solar system becomes almost unrecognizable. Out there, the sun is no longer a dominant presence. It is just another bright star in the sky, perhaps the brightest, but not overwhelmingly so. Its gravitational pull is faint, barely stronger than the tidal forces of the galaxy itself. Objects in the Oort cloud move incredibly slowly, completing orbits that may take millions of years. A single revolution can span epochs of Earth's history. Entire species rise and fall while one of these distant bodies completes a fraction of its path. And yet, despite this remoteness, the Oort cloud is thought to be tightly bound to the sun, not by strength, but by persistence. Gravity weakens with distance but never truly disappears. And over immense timescales, even weak forces matter. The Oort cloud represents the outermost reach of the sun's gravitational family, the final place where the sun can still say, "This is mine." We infer the existence of the Oort cloud from comets, long-period comets in particular, those that arrive from all directions not confined to the plane of the planets. Their orbits are nearly parabolic, suggesting origins far beyond the Kuiper Belt. When scientists traced these paths backward, they found a pattern, a spherical source, a reservoir of icy bodies surrounding the solar system. These comets are nudged inward by gentle disturbances, a passing star, a molecular cloud, the slow gravitational tide of the Milky Way itself. And that's the thing. The Oort cloud is not isolated. It is sensitive to the galaxy. It responds to forces far beyond the sun. And so, it serves as a bridge between the solar system and interstellar space, a place where the sun's influence and the galaxy's influence overlap. The objects within the Oort cloud are likely remnants from the earliest days of the solar system. When the giant planets were forming, they scattered vast numbers of icy bodies outward. Some were ejected entirely, becoming interstellar wanderers. Others were slowed just enough to remain loosely bound, forming this distant cloud. Over billions of years, these objects have remained in deep freeze, preserved in near-perfect isolation. Temperatures in the Oort cloud hover only a few degrees above absolute zero. Chemical reactions are almost non-existent. Time seems to stand still. And yet, these objects are not inert. They wait. They store potential. And occasionally they are awakened. When one of these bodies is disturbed and begins its long fall toward the sun, it becomes a long-period comet, a traveler from the deepest outskirts carrying pristine material from the dawn of the solar system. It may pass through the inner regions only once, shedding material blazing briefly, and then either escaping forever or returning to the cloud on an orbit that will take millions of years to complete. And perhaps that rarity is what makes these comets so evocative. When we see one, we are not just witnessing a spectacle. We are encountering something older than Earth itself, something that has spent most of its existence in darkness beyond comprehension. It is a reminder that the solar system's history is not confined to planets and moons, but extends far into invisible realms. The Oort cloud has never been observed directly. Its objects are too small, too distant, too faint. Even our most powerful telescopes cannot resolve them individually. And yet, its influence is real. Its presence is felt through the comets it sends inward. And in science, that is often enough. Effects reveal causes. Motion reveals mass. This unseen nature gives the Oort cloud a special character. It exists as a concept supported by evidence but still wrapped in mystery. Its size, its mass, its exact structure remain uncertain. Some models suggest it may contain trillions of objects. Others propose it is more sparsely populated. Its inner edge may overlap with the scattered disk. The boundaries blur, and that ambiguity feels fitting. This is the edge of what it means to belong to the sun. At such distances, the sun's gravity competes directly with the galaxy. The Milky Way exerts a tidal force that gently stretches the Oort cloud, altering orbits over millions of years. Passing stars can have dramatic effects. A close encounter can strip objects away entirely, or send showers of comets inward, potentially affecting the inner solar system. This has likely happened many times throughout Earth's history. Some scientists have speculated that periods of increased comet activity may correlate with mass extinctions on Earth. Whether or not this is true remains debated, but the idea itself is powerful. It suggests that events far beyond the orbit of Pluto, far beyond even the heliopause, could influence life on a small rocky planet billions of kilometers away. And that realization changes how we think about isolation. The solar system is not sealed, it is open. It interacts with its galactic environment in subtle but meaningful ways. The Oort cloud is where that interaction is most pronounced, where the sun's domain blends into the broader structure of the Milky Way. If you were somehow located within the Oort cloud, the night sky would look unfamiliar. The sun would no longer dominate. It would be just one star among many, perhaps brighter, but not dramatically so. Constellations would appear slightly distorted. Perspective would change. Distance, reshapes, identity. And I suppose there is something deeply poetic in that. To imagine our sun reduced to a point of light while still holding on to these distant icy companions, a quiet authority maintained across unimaginable distances. The Oort cloud also represents the final chapter of planetary formation. It contains material that was never incorporated into planets or moons. It is the leftover dust and ice from a process that began more than 4 billion years ago. In that sense, it is a museum of origins, a frozen archive storing the conditions from which everything else emerged. And yet, even here, the story does not end. Objects escape. The cloud evolves over long timescales. The Oort cloud may be gradually eroded, losing members to interstellar space. The sun itself is not static. It orbits the center of the galaxy, encountering different environments over cosmic time, and each encounter reshapes this distant halo. Eventually, billions of years from now, when the sun leaves the main sequence and transforms into a red giant shedding its outer layers, the fate of the Oort cloud will change dramatically. Many of its objects will be stripped away, others may be sent inward in dramatic bursts. But that future lies far beyond our current concern. It reminds us only that nothing in the universe is permanent. For now, the Oort cloud stands as the outermost structure of the solar system, defined not by light or wind, but by gravity alone. It marks the limit of what it means to belong to the sun. Beyond it lies true interstellar space, where the sun is just one star among many, and its influence fades into insignificance. And perhaps that is the final emotional note of this chapter. The solar system does not end with a dramatic boundary. It dissolves, it thins, it blends into the galaxy that gave birth to it. And the Oort cloud is where that blending becomes almost complete. As we drift outward beyond even this distant halo, we are no longer truly within the solar system. We are in the realm between stars, the space where new systems are born and old ones disperse. And yet, even as we cross that conceptual boundary, we carry something with us. Because one last thing still travels outward even now, beyond the heliopause, beyond the Oort cloud, beyond the sun's gravitational reach. Objects not of ice or rock, but of intention. Machines launched from Earth carrying fragments of our culture, our curiosity, our existence. And it is toward those silent messengers drifting alone into the dark that our journey naturally turns next, toward the farthest things humanity has ever created, still moving, still listening, still bearing witness at the very edge of our cosmic reach. Toward those silent messengers drifting alone into the dark. And here you see the story becomes quietly personal, because at the very edge of the solar system, beyond planets and comets, and even the last gravitational whispers of the sun, there is something unmistakably human, moving steadily outward without expectation of return. These are the Voyagers, the farthest things our species has ever touched. Voyager 1 and Voyager 2 were never designed to leave the solar system. They were built as planetary explorers, messengers of curiosity meant to visit Jupiter, Saturn, and beyond, during a rare alignment that occurs only once in many lifetimes. And yet, because of careful engineering and a bit of cosmic generosity, they became something else. Entirely by accident, they became interstellar pioneers. These spacecraft are small by cosmic standards, roughly the size of a car, built with technology that now feels almost antique, and yet they have endured radiation, cold silence. They have traveled for decades without repair, without guidance beyond faint commands whispered from Earth. And they continue on. Still, Voyager 1 and Voyager 2 are the most distant human-made objects ever created. No probe, no signal, no artifact has traveled farther. Their distance from Earth is so great that radio signals moving at the speed of light take many hours to arrive. Each conversation with them is delayed. Each response is a relic from the past, and that alone reshapes how we think about communication. When we send a command to Voyager, we are not speaking to the present. We are speaking to where it was many hours ago. And when it replies, we receive a message from a time that has already passed. Conversation becomes archaeology. Even now, as they drift deeper into interstellar space, their signals grow weaker, fading into the cosmic background. Yet they persist. The Voyagers cross the heliopause one by one, marking humanity's first direct contact with interstellar space. And they did so silently. There was no celebration at the spacecraft, no awareness of the milestone, only a shift in particle counts, magnetic field orientations, and cosmic ray intensities. But here on Earth, those subtle changes were understood as something monumental. A species bound to one planet had extended its reach beyond its star. And I suppose that moment carries a profound humility. These machines are not alive. They do not know they are pioneers. They carry no flag, no voice, no claim. They simply continue because physics allows them to continue, and in that continuation lies a quiet dignity. Perhaps the most evocative aspect of the Voyager missions is what they carry with them. Each spacecraft bears a golden record, a time capsule, a message in a bottle sent into the cosmic ocean. The record contains sounds, images, music, and greetings from Earth. A child laughing, a heartbeat, waves breaking on a shore. Greetings spoken in dozens of languages, music spanning cultures and centuries. It is not a message sent with expectation of reply. It is an act of hope, a statement that we existed, that we wondered, that we listened. And perhaps that is the most human thing we have ever done, to send a representation of ourselves into the unknown, not for conquest or survival, but for connection. The golden record does not explain our politics or our conflicts. It does not capture our fears or our failures. Instead, it offers a glimpse of our shared humanity, our curiosity, our art, our sense of beauty. It is a humble offering, saying simply, "This is who we were," and that raises a quiet question. Who was this message really for? It may never be found. The chances are extraordinarily small that any other intelligence will ever encounter these spacecraft. But perhaps that is not the point. The act itself matters. It reflects how we see ourselves, not as conquerors of space, but as participants in a vast universe. We are only beginning to understand. Voyager 1 and 2 continue to send data even now, measuring the density of interstellar plasma, detecting magnetic fields, sampling cosmic radiation. They are our eyes and ears beyond the sun's protective bubble, and each bit of data they return expands our understanding of where we truly are. The environment they now travel through is stark. Interstellar space is not empty, but it is unforgiving. The density of matter is extremely low. The radiation environment is harsh. The temperature is defined more by particle energy than warmth. And yet, this is the normal state of the universe. Most of existence unfolds under these conditions. The Voyagers will not last forever. Their power comes from radioactive sources that slowly decay. As their energy diminishes, instruments fall silent one by one. Eventually, there will be no electricity left to transmit signals, and the spacecraft will become mute. Objects drifting endlessly without voice. But even then, their journey does not end. They will continue moving, following trajectories set long ago. They will orbit the center of the Milky Way along with billions of stars, passing near other stellar systems over timescales that defy imagination. In a sense, they will outlive Earth as we know it. And that thought can feel unsettling but also strangely comforting. These machines are extensions of us. They carry a trace of our existence forward even when we are gone. They remind us that our actions echo beyond our lifetimes, sometimes far beyond. The Voyagers also redefine what it means to explore. Exploration is not always about arrival. Sometimes it is about departure, about letting go, about allowing something to move beyond our reach. They teach us that exploration can be patient, quiet, and long-term, measured not in headlines, but in decades. When we consider how far they have traveled, we are forced to confront scale again. The solar system is vast. The distance to the nearest star is staggering. And even now, the Voyagers have barely begun the journey between stars. They are not heading toward a destination. They are simply leaving. And perhaps that is the most honest metaphor for humanity's relationship with the universe. We are not yet explorers in the grand sense. We are learners, tentative, careful, sending out small pieces of ourselves into the unknown, hoping to understand a little more. The Voyagers have also changed how we see Earth. The images they sent back from the outer solar system show our planet as a pale dot suspended in a sunbeam, fragile, isolated, and profoundly precious. That perspective did not come from philosophy or poetry. It came from distance, from stepping far enough away to see ourselves clearly. And that perspective lingers. It reminds us that everything we value exists on that small world. All our stories, all our struggles, all our love. It is easy to forget that when we look outward. But the Voyagers carry that reminder silently into the dark. Even now, as you listen to this story, they continue on. Their signals faint but present, each one a whisper from the edge of human reach. And someday those whispers will stop, not with drama, not with finality, just with silence. And yet the journey will not truly end. Because long after the last signal fades, the spacecraft will remain, carrying their golden records, their instruments, their scars of travel. They will become artifacts of a civilization that once looked up and wondered. And in that sense, the Voyagers are not just machines. They are questions made of metal and code. Asking, who are we? Where do we belong? What does it mean to reach outward? As we stand at the edge of the solar system with them, we are invited to think not just about distance, but about meaning. The sun is one star among many. The solar system is one island in a vast cosmic ocean, and we are only beginning to learn how to sail. Beyond the Voyagers lies nothing familiar, no boundaries, no maps, only the galaxy stretching endlessly in all directions, filled with stars, planets, clouds, and mysteries we have not yet imagined. And perhaps that is the most honest ending to this journey, because reaching the edge of the solar system does not answer our questions, it deepens them. It reminds us that science is not a path toward final certainty, but a conversation with the unknown. Each discovery opens new horizons. Each boundary becomes a threshold. And as the Voyagers drift onward into the dark, carrying our curiosity with them, we are left with a quiet realization. We are not at the end of anything. We are at the beginning, still learning how to listen, still learning how to wonder, still taking our first careful steps into a universe far larger and more beautiful than we ever expected. Still taking our first careful steps into a universe far larger and more beautiful than we ever expected. And from here, you see the question changes subtly. It is no longer only where does the solar system end, but what does that ending mean? And perhaps more importantly, what lies beyond it? The edge of the solar system is not a wall. It never was. It is not the end of motion or matter or influence. It is simply the place where one story gives way to a larger one, where the familiar grammar of planets and orbits dissolves into the broader language of the galaxy. And when you truly sit with that idea, it reshapes everything. Beyond the sun's last gravitational whispers, beyond the heliopause and the faint halo of the Oort cloud, The universe continues. Uninterrupted interstellar space is not empty. It is threaded with gas and dust, magnetic fields and radiation. It carries the raw ingredients of future stars and planets. It is both the graveyard of old systems and the nursery of new ones. And that's the thing. The solar system is not separate from this environment. It emerged from it, and it will one day return to it. Our sun, for all its importance to us, is an ordinary star, one among hundreds of billions in the Milky Way. It follows a slow orbit around the galactic center, carried along with countless others, born from the collapse of a cloud enriched by earlier generations of stars. And one day, it too will contribute its material back to the galaxy. In that sense, the solar system is a temporary arrangement, a beautiful and intricate one, but not permanent. And yet, during its lifetime, this small island of gravity and light became a place where complexity flourished, where chemistry learned to think, where matter arranged itself into beings capable of curiosity. That alone gives it meaning beyond its size. When we talk about the edge of the solar system, we are really talking about perspective. Standing inside it, the sun feels central, dominant, eternal. Standing outside it, the sun becomes a point of light among many, and neither view is wrong. They are simply different frames of reference. And perhaps wisdom lies in holding both at once. The journey to the edge of the solar system has taught us that boundaries in nature are rarely sharp. They are transitions, gradients, zones where one influence slowly yields to another. The solar system fades into the galaxy, not abruptly but gently, and that gentleness is important. It tells us that belonging is not binary. You do not suddenly stop being part of something. You gradually become part of something larger. Each discovery we have made on this journey has opened new questions rather than closing old ones. We found that planets are not the only worlds of interest, that moons can be active and potentially habitable, that icy bodies preserve ancient histories, that invisible forces like solar wind and magnetic fields shape vast regions of space. And each time we thought we understood the structure of our home, it grew larger, more complex, more subtle. The solar system turned out not to be a neat clockwork, but a living, evolving system, still settling, still interacting, still changing, its planets migrated, its small bodies scattered, its boundaries breathed in and out. And in learning this, we learned something about science itself. It is not a collection of answers, it is a way of listening. Perhaps that is why the silence at the edge feels so powerful. Out there, beyond the last signals of Voyager, there is no sound, no warmth, no immediate response. And yet, it is not empty. It is full of potential, full of histories unfolding on scales we are only beginning to imagine. From this vantage point, Earth becomes astonishingly precious, a small world orbiting an unremarkable star in a quiet arm of a spiral galaxy. And yet, everything we have ever loved exists there. Every memory, every thought, every question. That realization does not diminish us. It deepens our responsibility. The farther we travel from Earth, the more clearly we see it. Not as a center of the universe, but as a rare oasis, a place where matter became aware of itself. And perhaps that is one of the quiet gifts of exploring the edges. It teaches us humility without despair, awe without insignificance. The solar system is a small island. Yes, but islands matter. They are places where complexity can arise, where isolation allows uniqueness to flourish. And just as islands on Earth are shaped by the surrounding ocean, the solar system is shaped by the galaxy that surrounds it. And so, touching the edge of the solar system is not about reaching a finish line. It is about realizing that every boundary is an invitation to look outward and inward at the same time, to ask not only what is out there, but who are we in relation to it. The universe does not end at the heliopause. It does not pause at the Oort cloud. It stretches on for billions of light years filled with structures. We are only beginning to map galaxies cluster and collide. Black holes sculpt space-time stars are born live and die, enriching the cosmos with the elements of possibility. And somewhere within that vastness, a small species on a small planet learned to ask questions, learned to build instruments, learned to listen to the quiet. And that may be the most extraordinary fact of all, because the journey to the edge of the solar system ultimately turns us back toward ourselves. It asks us to consider what kind of explorers we wish to be, whether we approach the unknown with fear or curiosity. With conquest or reverence, science does not end at boundaries. It begins there. Each edge we reach becomes a new starting point, a deeper question, a wider horizon. And perhaps that is why the universe feels endlessly compelling. It does not offer closure. It offers continuity. As we stand conceptually at the edge, with the sun now just another star behind us and the galaxy opening ahead, we are reminded that our story is still young. Our tools are still simple. Our understanding still partial. And yet we are here. We are listening. We are wondering, and that, I suppose, is enough to begin again to take the next step outward into a universe that does not ask us to conquer it, only to understand it a little more deeply. Each time we dare to look beyond the horizon. To look beyond the horizon. And as we do, something subtle happens. The journey outward, step by step, from the warmth of the sun to the quiet edges of its influence, begins to fold back in on itself. What started as a voyage through space becomes a voyage through meaning. And perhaps that was always inevitable. When we speak of the edge of the solar system, we are tempted to imagine a destination, a final point, a moment of arrival. But the universe does not work that way. There are no finish lines written into space-time, only gradients, only transitions, only stories that widen as we follow them. And you see, the farther we travel from the sun, the clearer that truth becomes. The solar system does not end. It thins. It loosens. Its structures dissolve into probability. The planets give way to debris. The debris gives way to icy halos. The halos give way to interstellar space. And even there, nothing truly stops. Motion continues. Gravity whispers. Light travels. Time unfolds. And that quiet continuity is perhaps the most important lesson of all. Beyond the edge of the solar system lies not emptiness, but connection. Interstellar space is filled with the same atoms that once formed stars like our sun, the same elements that make up our bodies, drifted once through ancient supernovae before finding temporary shelter in planets and people. The boundary we crossed is not a separation. It is a reminder that everything belongs to something larger. Our sun is not unique. It is not special in isolation. And yet, within its modest sphere of influence, something extraordinary happened. Matter organized itself into complexity, into awareness, into beings capable of tracing the outline of their own cosmic neighborhood, and that is the quiet miracle. Science does not diminish wonder. It reveals it. When we learn that the solar system has no sharp edge, we also learn something about ourselves. We learn that certainty is rare, that clarity often emerges gradually, that understanding is not a moment, but a process, and perhaps that is why exploration feels so deeply human. It mirrors the way knowledge itself grows. The farther we push outward, the more the universe invites humility. Our star is one among many. Our planet is small, our species young. And yet, within that humility lies empowerment, because understanding our scale does not erase our significance, it reframes it. A single human lifetime is fleeting compared to the orbits of comets or the slow tides of the galaxy, but meaning is not measured in duration. It is measured in awareness, in the ability to ask questions, to seek patterns, to care, and in that sense, even brief moments matter. The solar system, once imagined as a tidy clockwork, revealed itself to be a living dynamic structure. Planets migrated, moons reshaped, icy bodies scattered, winds blew bubbles in space, boundaries breathed, and nothing stood still. And that realization echoes far beyond astronomy. It reminds us that change is not failure. It is nature's default state. When we followed the solar wind to its fading edge, we learned that protection can be invisible, that forces we cannot see shape the conditions for life. When we traced comets back to distant clouds, we learned that the past never fully disappears. It waits preserved until disturbed. And when we listened to the faint signals of Voyager, we learned that exploration is as much about patience as ambition. The Voyagers themselves embody this lesson. They are not triumphs of speed or power. They are triumphs of persistence, of careful thought, of trust in physics and time. And they continue outward, not because anyone commands them to, but because the universe allows them to. And perhaps that is the most honest metaphor for science. We do not force the universe to reveal itself. We follow where it leads, we listen, we wait, we adjust our understanding. And slowly, the picture sharpens. The edge of the solar system is also the edge of familiarity. Beyond it, our intuition begins to fail. Distances lose meaning. Time stretches, concepts blur, and that discomfort is valuable. It tells us we are learning something new. It tells us we are leaving the safety of assumption. Standing at this conceptual boundary, with the sun now reduced to a bright star behind us and the galaxy opening ahead, we are invited to reconsider what it means to belong. The solar system is our home. Yes, but it is also a temporary address, a chapter in a much longer story. One day, billions of years from now, the sun will change. It will swell and shed its outer layers. Its planets will be altered or destroyed. The Oort cloud will be disturbed, and the solar system as we know it will dissolve. But the atoms that once formed it will not vanish. They will return to the galaxy. They will seed new systems, new possibilities. In that sense, endings are not losses. They are transformations. And the universe is generous with second chances. The journey to the edge of the solar system teaches us that knowledge does not shrink mystery. It deepens it. Every answer opens a wider question. Every map reveals a larger unknown. And perhaps that is why the pursuit of understanding never feels complete. Because completion was never the goal. We are not meant to arrive at final truths. We are meant to participate in the slow unfolding of comprehension, in the dialogue between observation and imagination, in the shared effort to make sense of a universe that does not owe us simplicity. And there is something profoundly comforting in that. The universe does not rush. It does not demand certainty. It allows us to explore at our own pace, to make mistakes, to revise our stories, and over time, those stories grow closer to reality. As we look back inward from the edge, Earth appears fragile and luminous, a small world suspended in darkness, and everything we value is there. All our histories, all our hopes, all our futures, and the knowledge that there is no second Earth waiting just beyond the horizon changes how we see responsibility. Exploration is not an escape from home. It is a way of understanding why home matters. The silence at the edge of the solar system is not empty. It is reflective. It gives us space to listen not only to the cosmos, but to ourselves. To ask what kind of explorers we want to be. What kind of stewards? What kind of storytellers? Science at its best is an act of humility. It says we do not know, yet it invites collaboration across generations. It builds understanding brick by brick, and it trusts that even incomplete, knowledge is worth pursuing. The solar system, as vast as it feels, is only a small island in a much larger cosmic ocean. And yet, islands are places where stories begin, where navigation is learned, where courage takes its first steps onto open water. Touching the edge of that island does not mean we are ready to cross the ocean, but it does mean we are curious enough to look. And that curiosity is our greatest inheritance. Every generation adds a little more to the map, a little more to the story, and the map is never finished. The story never closed. That is not a failure of understanding. It is its defining feature. As we drift conceptually beyond the solar system, the universe does not become colder or more indifferent. It becomes more intricate, more layered, more alive with possibility. And perhaps that realization is what keeps us looking up. We are not separate from the cosmos. We are a way for it to know itself, to reflect, to ask. And even at the edge of our home system, that truth holds steady. The sun will continue to shine. The galaxy will continue to turn. Stars will be born and die. And somewhere, perhaps on a small world orbiting a distant star, other beings may one day ask the same questions we do. Where does our home end? What lies beyond? And what does it mean that we can ask at all? The journey to the edge of the solar system does not conclude with certainty. It concludes with perspective. It leaves us not with answers carved in stone, but with a deeper sense of belonging to something vast and unfinished. And perhaps that is the most fitting ending. Not closure, but continuation. Not an end, but an opening. A quiet invitation to keep listening, to keep wondering, to keep moving gently outward into a universe that does not demand our understanding, only our attention. Because in the end, the greatest discovery is not how far the solar system extends, but that we are part of a story still being written, one that stretches far beyond our horizon, and asks us, softly but persistently, to take the next step into the unknown.